In this video, we're going to talk about Fischer esterification, a really interesting reaction where you're transforming a carboxylic acid into an ester, lots of different esters. These often smell really fruity and amazing, and they're fantastic labs. All right, so let's go into it. First, let's answer a question about what you might be having is why not just use OR minus, as we've seen in acyl substitution chemistry, for example, a trans esterification. Why not just treat this as we've seen before? Well, if you treated a carboxylic acid with OR minus, you would simply deprotonate the carboxylic acid and you'd wind up with a carboxylate. And if you remember from a previous video, carboxylates are really stable. So that's not a good approach to making an ester. All right, so let's look at what we do use. So we typically use an alcoholic solvent, for example, methanol, ethanol, isopropanol, whatever you want for your alcohol will wind up as your ester, and you do this under acidic conditions. So you're going to see a new type of reaction today, reactions under acidic conditions. You'll notice that this reaction also generates an equivalent of water in the process. So typically these reactions are done in a manner to remove water from the reaction. We generally use strong acids, for example, sulfuric acid, for these types of reactions. And the first question that we have to ask ourselves, and we'll see this later in the mechanism, is where do we protonate on these substrates, or on these acids? So you can either protonate on the oxygen atom, this one, the acidic oxygen atom, or on the carbonyl oxygen atom. And I'll point out, this is one of the things I like about this mechanism, is that you are starting with a carboxylic acid, and the carboxylic acid is actually acting as a base in this case, because sulfuric acid is significantly more acidic. So sulfuric acid is protonating your acid. So your acid is further acidified. And so if you look at the difference between these two structures, the structure on the right has resonance structures or a resonance structure that can stabilize and share the burden of the positive charge on the oxygen atom across multiple oxygen atoms. So again, in this case, your resonance is stabilizing because you're sharing the burden of a charge. In the case of this structure on the left, there is no such resonance structure, and so there is no help for this burden. So therefore, you protonate on the carbonyl oxygen. And this is a very common occurrence you'll see in lots of carbonyl mechanisms under acidic conditions. You protonate the carbonyl oxygen as opposed to the atom down here, simply because there are resonance structures that can stabilize this type of species. Let's go ahead and look at the mechanism. So again, we have acetic acid in this case, and ethanol, and we're going to form ethyl acetate, the ethyl ester of acetic acid, using sulfuric acid. We often, when we're drawing sulfuric acid or strong acids, we can simplify this as drawing simply H+. This will simplify your mechanism. So we protonate where we said we were going to protonate on the carbonyl oxygen, and we confidently draw our arrow from the electrons to the positively charged H+. And we wind up with this protonated carboxylic acid structure here. Now we can use ethanol as our nucleophile and react with the electrophilic carbon, and those electrons from the pi bond go onto the oxygen atom. So this is very similar to what you saw in the nucleophilic acyl substitution reaction before, the difference being that there are no negative charges involved, only positive charges, and that's because we're under acidic conditions. So keep positive charges under acidic conditions. Acids are positive. This gives us a tetrahedral intermediate, again very similar to the acyl substitution tetrahedral intermediate, except the difference is in the acyl substitution we had negative charges, here we have positive charges. So right now we need to make this, the ethanol that added in needs to lose its proton, so we can have solvent, in this case ethanol, remove the proton, and we can also now have one of these two oxygen atoms get protonated from the acid in solution. We refer to this kind of process as a proton transfer, and I'm okay with you simply writing PT to go from this type of structure to this structure. Once you've done this proton transfer, you've generated a good leaving group in the form of water. So now water is a good leaving group. It can leave the molecule as a neutral water molecule. You're not generating any negative charges, so that's good. You're under acidic conditions. And you can wind up with this type of carbocationic intermediate here. I'll point out that this, a lot of people like to also draw this type of arrow mechanism drawn in purple, where you have the electrons on one of the two oxygen atoms kind of pushing down to form a carbonyl and kicking off the water molecule to directly give you this protonated carbonyl species here. What I'd like to point out real quickly is that these two structures are simply resonant structures of each other. Whichever way works better for you to think about how these molecules or these reactions work is a good way of thinking about it. I've drawn both of these simply to show that, again, they're resonant structures, so they're two images of the same structure. Whichever works better for you is the way to do it. So now you have a protonated carbonyl that looks a lot like your final product, but we don't, as organic chemists, when we're drawing mechanisms, we don't like to wind up with a positively charged or negatively charged structure. So we simply we could use the water that we just kicked off to deprotonate the carbonyl and give us now our ester. We've now regenerated some acid that can go back into the whole cycle, so you can use catalytic acid. Again, we formed the ester. Now this mechanism has lots of mechanistic steps, and I'm going to talk about some of them here. I like to sometimes keep track of where the atoms are that we're dealing with, and so this oxygen atom of ethanol is the same oxygen atom that is found in your final product, in the ester of your final product. I'll also point out that all of these steps are actually reversible. So if you ran this reaction starting with an ester and you wanted to go back to a carboxylate, you can do that. You would not run that reaction in ethanol, you would simply run that reaction in water to push the reaction the other direction. A question I sometimes will get is, why didn't I pick the other oxygen atom here? And actually, they're both identical at this point. I simply chose this one, but I could have chosen the other one on the left. So either of these two oxygen atoms are identical at this stage, and they could get scrambled in the reaction. So there are some common and very tempting errors associated with the Fischer esterification. The first is that you will skip the protonation step at the beginning of the mechanism, and you'll wind up with an alkoxide. That's not acceptable because you're under acidic conditions, so do not have a very strong base in the presence of a strong acid. Not okay. Another very common and tempting mechanism is to have protonated ethanol and use your carboxylate, or your carboxylic acid rather, as the nucleophile to kick off water as a leaving group. The problem is that this is a weak nucleophile. It's a very weak nucleophile, and we can discuss why that's the case at some other time. Another tempting mechanism is to protonate on this other oxygen and use ethanol as a nucleophile and simply kick this off in one step, avoiding all of the annoying hassle of the tetrahedral intermediate. That tetrahedral intermediate is incredibly important and should not be avoided. But that's not why we're doing it, or why we don't avoid it. We don't avoid it because, again, this is not where this molecule protonates. It protonates in the carbonyl oxygen. The second point is that this is not the weakest bond. So if you're adding this ethanol, you wouldn't be breaking this bond. You'd be breaking the pi bond. A third point is that the sterics and the trajectory of this ethanol adding in is not conducive to a good reaction. Again, it is a sterically congested trajectory, or again, the way the molecule would have to approach the nucleophile would have to approach the electrophile. So for all of these reasons, this is not a good approach. So I will hope that you will not use any of these common arrow-pushing errors. And again, they're tempting, but avoid using them. All right, well, that is all for today's talk about the Fischer esterification. I hope you have questions in class. Thanks.